Okay, in this video I'd like to continue on with my tutorials in thermodynamics and statistical mechanics. This is video number 33 and this is the sub-video 2 for the two-state paramagnet. So the previous video to this of course is the two-state paramagnet number 1. So what's the point? The point of this is that we want to use the process of calculate the heat capacity, which is described in a previous video, whereby you get the multiplicity, you get the entropy, you get the temperature, you get the energy, and then finally you get C sub V is del U del T. Right, that's what we want to do, just to prove it. Okay, and we saw a lot of the interesting physics in the first video. So this one is going to be nothing new. So if you just want to know about the physics, look at video number 1 and look at video number 32, we'll say, and carry on to video number 34 if you like. However, if you'd like to see how this is done analytically, well then this is the video to watch. However, it's quite tedious, I must admit. So I'm going to get cracking because, like I said, it is tedious. So the first thing we need to do is to get some sort of an expression for the multiplicity. Now we got an expression for the multiplicity earlier on. Okay, so the multiplicity for a two-state system is very straightforward. Okay, and we saw this in my videos on Einstein Solids. So the multiplicity for the system being in the up state is equal to the total number of dipoles factorial, the number up factorial, and the number down factorial. Okay? Now, where are we going to go from here? Well, we need to get the entropy. Alright? So we need to get basically the S is equal to K times the natural logarithm of the multiplicity. But before I do that, I just want to do two quick results that we're going to need later on, which once I've showed them, you can just note them in your head, because we'll be using them at some stage. The first one is this: the number of up minus the number down is equal to minus u over mu times b. We showed that in video 1. Now we also know, of course, that the number total is equal to the number up plus the number down, or that the number up is equal to n minus the number down, or the number down is equal to n minus the number up. Okay? So if you plug that in here, we get the following. The number down, the number up is equal to the total minus u over mu times b divided by 2. And finally, the number down is equal to, of course, by symmetry, the total number plus u over mu times b divided by 2. So will you please note those two? We'll be plugging them in later on. Okay, so that's all we need to say about that. So look, that's pretty straightforward algebra. Next, the total energy, as we showed in the previous video, was as follows: u is equal to mu times b, and it's n minus twice n, and it's twice n up. Okay, well we can rearrange this for n up as follows: mu times b times n minus u over twice mu b. Okay, and you'll see later on that at some stage we're going to be getting the derivative with respect to u of the number of dipoles pointed up. And if you look, it's pretty straightforward. It's minus 1 over 2 u b. Now look, I did that very quickly because it's pretty straightforward. Okay, and that did just some bits of algebra that we need later on. So let's go to the start again. We had that the multiplicity is equal to the total number factorial, the number down factorial, and the number up factorial. So we need to get S is equal to K natural logarithm of the multiplicity. Now, what are we going to use here? Of course we're going to be using Stirling's approximation. So that A factorial, the natural logarithm of A factorial, is equal to A log A minus A. And I proved that in a previous video. Just bear with me and I'll tell you which one. It's number 11. In video number 11 I proved Stirling's approximation. Now if we know our rules of logarithms, we know that if we take, let's say, s over k, okay, is going to be equal to the logarithm. Now look at it, it's going to be the logarithm of n factorial minus the logarithm of n down factorial minus the logarithm of n up factorial. Okay, that's just the rules of logarithms. So in each one of these I'm going to apply Stirling's approximation. Very straightforward, and you'll find most of them cancel. for that reason I'm not going to write them down, but I am going to write down the result. So very quickly, by applying that, we can get the functional form of the entropy, namely that it's Boltzmann's constant outside the following: capital N log capital N, that's the total number of dipoles, minus n up log n up, minus n up log n minus n up. Okay. Now, you might be wondering, well, where did that come from? How come there's an n minus n up? Well, think about it. N down, if you like, can be written as n minus n up. N minus n up, like that. Okay. So if you write it that way, in other words, put everything in terms of the total number of dipoles and the total number of dipoles pointed up, we get the following expression. Great stuff. Now, remember, what do we need to get? We need to get the multiplicity, get the entropy, and after that we need to get the temperature. We know that 1 over the temperature is equal to del S del U. Now the thing is, look at S. What is it a function of? Well, it's a function of the total number, and it's also a function of the number pointed up. Okay, so we need to use the chain rule. So del S del U, okay, first of all it's going to be del S del N up del U, and of course we're also going to get del S, that's it. Okay, that's all we're going to need. So where do we go from here? Well, we just start plugging and chugging. Okay, so let's go ahead and do it. So we have our chain rule. Okay, so what I'm going to do first of all is del S del N up, del S del N up here. I'm going to get this. Now here is, that's our functional form of entropy. So you need to get the derivative with respect to N up on this. That's pretty straightforward. So del S del N up is going to be equal to the following. Well, of course we're going to have Boltzmann's constant on the outside, and if you look at it, right, well, not dependent on N up. This one here is dependent on N up, and we're going to get, well, it's a chain rule, of course. No, sorry, it's a product rule, of course. So we're going to get the natural logarithm of N up times plus 1, which we're not going to write down, and then UV minus UdV minus VdU, or it's actually UdV plus VdU, I suppose, isn't it? And then we're going to have N up over N up, like that. That's the end of the product rule. Something similar here, in fact. I'm just going to write down the answer. Okay, so we're going to have N minus N up divided by N minus N up minus the logarithm of N minus N up. But there's also a minus 1 here as well, like that. Okay, close it all off. Now I just want to make sure that you can see that. Yeah, you sure can. Okay, so we can see that can be simplified in a very straightforward manner. So del S del N up is going to be equal to Boltzmann's constant outside of, well, there's going to be a logarithm, of course, N minus N up divided by N up, which is K log N down over N up. Now you might say, well, okay, why is that good to us? You remember the two formula? Hopefully you may remember or recall at the very start I had I manipulated the two of those and I got the following: del S, and rewrite this by using the formula I had at the start, then up is equal to K log N plus U over mu B over 2, and then under that we're going to have N up, which is N minus U over mu B over 2. Like that. Looks a bit hairy, but you can see there's lots of symmetry and all these things cancel out. We're going to get K log N plus U over mu B n minus u over mu b. And now we have a formula for del S del n up. Now you might say, it's looking mad, but really it's not. It's just a bit of algebra. So finally, to go back up to here, we need to get del n up del u, but in actual fact I got that at the start. That was one of the derivatives I got at the start. So if you multiply that derivative, which was equal to minus 1 over 2 mu b, you multiply it by this, and then that is equal to 1 over t. And you're just going to write down the answer, okay? It's going to write down the answer, so you're going to have to accept it or do it yourself. Okay, so this is a very, very small bit of manipulation, but we can rewrite 1 over the temperature as equal to Boltzmann's constant divided by twice mu b. And then we have n minus u over mu b, and we have n plus u over mu b. Like that. Sorry, there's of course a logarithm in here. And that is 1 over the temperature. So now we have the temperature. Okay, so what's the next? What's the next step? Well, the next step, of course, is to get u in terms of T, N, V, S, or whatever else. But if you look at it, really, all we're rearranging is, we're just rearranging this for u. Okay, rearranging this for u. So I'm going to delete a lot of the things up here, which we no longer need. So what we have is as follows. We have 1 over the temperature is equal to k outside of the natural logarithm of n minus u over mu b n plus u over mu b. Okay, now I'm going to give you some, I'm going to call the following. I'm going to say that d is equal to 2 mu b over kt, and c is equal to u over mu b. Okay, cd, and there's another one, b is equal to k over mu b. And I'm actually forgetting there's 2 mu b here as well. Now, okay, so look, it's just algebra. Algebra is just a bit of a pain. So if we rewrite that, if we look at the argument up here, that means the argument the whole thing becomes n minus c over n plus c is equal to e to the d. Okay, by getting rid of our logarithm by taking an exponential. Very straightforward. Rewrite that as n times e to the d plus c times e to the d is equal to n minus c. Okay? Now, if you rearrange that for u, which is in here, which is basically rearranging for c, so we need to get c, and I'm telling you, just you can do the rearrangement, and you're going to get u over mu b. So c is equal to u over mu b, or u is equal to, and by the way, I just may as well write that out where that came from. That was 1 minus e to the d divided by 1 plus e to the d. Okay, went like that. Alright, so finally u is equal to u b n 1 minus e to the d 1 plus e to the d, like that. Okay, and you can put in the placeholders if you like, no big deal. What I'd like to notice here is that the placeholders are 1 minus e to the d, 1 plus e to the d. Okay? So why is that important? Well, I think it's time that I put in the full answer. So I'm going to put it in without my placeholders. I'm going to rewrite that equation. So we had u is equal to mu b n. 1 minus e to the 2 mu b over kt. 1 plus e to the 2 mu b over kt. Like that. Now, here's a trick. You should perhaps know this, that if we define the hyperbolic sine as e to the x minus e to the minus x over 2, and the hyperbolic cosine as e to the x plus e to the minus x over 2, and to find the hyperbolic tangent as normal as sine over cos, we're going to get the following. You get the hyperbolic tangent, that should be cos, excuse me, is equal to 1 plus e to the 2x over 1 minus e to the 2x. Look what we have here. We have pretty much the same thing. However, of course, there's this negative sign. So essentially, this is a hyperbolic tangent. Now, how somebody sees that, to be honest, is a bit beyond me. But anyhow, so we can look at it that way. So let's do the following. If we, sorry, there was a minus sign there. Sorry, minus. That was. I may as well just write it out. Minus tan x. Okay, that's minus tan hyperbolic tangent. Like that. So, this here can be rewritten, the whole thing can be rewritten as u is equal to minus mu bn, the hyperbolic tangent of mu b over kt. Oh, kt, come on, kt. Full stop. Now you might be wondering, where did the factor of 2 go? Well, the factor of 2 is part of the hyperbolic tangent, so that's where it went to. So that means that our energy function is actually a hyperbolic tangent. What does that look like? Well, it's a bit of a weird function, because it's plus 1 here, this is minus 1 of course, and the hyperbolic tangent has an asymptote, a plus and minus 1, and it looks something like this. So now we have the functional form of the energy. So you might be getting bored, maybe you've turned it off at this stage, I'm not too sure, but I'm going to finish it out anyway. So the next thing we need to do is get the heat capacity. Well, the heat capacity is pretty straightforward because it's del U del T. So what we have is as follows. We need to get C sub V is equal to del T of minus mu b n hyperbolic tangent mu b over kt. Boom. Okay? So look, it's just a small bit of differentiation. Now we know that, for example, the hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine. Now, I'm not going to really go into it, but the cos squared, you're going to get terms of cos squared and hyperbolic sine squared and so on. And we know that cos squared plus sine squared is equal to 1. So basically what's going on, to be honest, I'm not even going to do it because it's pretty straightforward, right? But you're going to get the following. You're going to get ddt of, actually, sorry, the whole thing actually, the ddt of u is going to be equal to minus mu bn minus mu b over kt squared 1 over, whoa, we're getting mad now, cos squared mu b over kt. Now if you multiply above and below by k, we can rearrange it into a nice looking form such that C sub v, the heat capacity at constant volume, is equal to capital N times k mu b over kt to be squared 1 over cos squared mu b over kt. Now that was a pain in the face, and I know, but we'll see later on when we start doing quantum statistics that we can do all of that in about 3 lines. Okay, so look, there was me grinding out exactly how you calculate the heat capacity at constant volume right from your multiplicity. So thanks for watching. Please pass it on to your friends and subscribe to my channel. Now if you're still here, you might also click on an ad. Thank you.